Good morning, my dears. So today I am going to discuss about semi-empirical mass formula. Okay, so yesterday we have discussed about NZ graph in our first class and next liquid drop model in our second class. So today I am going to discuss you about semi-empirical mass formula. So this formula was proposed by Weizsäcker. Okay, the scientist Weizsäcker. Okay, so this semi-empirical mass formula was proposed by Weizsäcker, and according to Weizsäcker, what is binding energy means the energy is required to remove the total number of nucleons. For example, this is a nucleus consisting of positive charge, and the amount of energy required to remove the nucleons, that is protons and neutrons, from the nucleus. Okay, from the nucleus, that is from binding state to free state. This required amount of energy is called as binding energy according to Weizsäcker. The amount of energy required to separate the nucleons from the nucleus. The amount of energy required to separate the nucleons from the nucleus is called binding energy. That is, we are changing the binding state to the free state. Okay, so this is what about the binding energy. This is also called as nuclear binding energy. Okay, so now this nuclear binding energy is depending on the different factors. Okay, I am writing here. Okay, so now this nuclear binding energy depending on the following terms. Those are, first one is volume energy term, and next surface energy term, Coulombic energy term, asymmetric energy term, and next pairing energy term. So first I would like to discuss about the volume energy term. First one is volume energy term. So volume energy term means, in general, what is the volume of the nucleus? What is the volume of the nucleus? Nucleus is spherical in shape, so that is why the volume of the nucleus is, for example, let us consider a nucleus which consisting of a radius r. Okay, then the volume of this nucleus is V is equals to 4/3 pi r cube. Okay, 4/3 pi r cube. This is the volume of the nucleus. So now what is the radius of the nucleus? Already I told you in the previous classes, that is the radius of the nucleus is r is equals to r naught into a power 1/3. R is equals to r naught into a power 1/3. Now you substitute r value in this above equation, that is V is equals to 4/3 pi r naught a power 1/3 whole cube. This is V is equals to 4/3 pi r naught cube into a. Okay, this is what the volume of the nucleus. Now see here, 4/3 pi r naught cube is constant, right? Now here the volume of the nucleus is directly proportional to the mass of the nucleus. That is a here. A means what? Mass of the nucleus. The volume is completely depends on the mass. If the volume increases, then what will happen? The mass number is also increases. Then the stability of the nucleus is decreases. Volume increases, mass number increases. Then the stability what? The stability of the nucleus is decreases. If the volume of the nucleus is increases, then the stability of the nucleus is decreases. Then finally the volume energy term. Here see, the volume energy term is directly proportional to the mass number. Here I am writing the volume energy term is denoted by EV. EV is a volume energy term, is directly proportional to A. Okay, if I remove the proportionality, it is EV is equals to, let us say the proportionality constant is A into A is our mass number. This is what volume energy term. Okay, keep it aside. Now coming to the second, surface energy term. Okay, surface energy term. In this case, what will happen? In the liquid drop model, already I told you. Okay, in the next video we will discuss about the surface energy term. Thank you.